Let me get started by first announcing that in the afternoon, what we're going to do for the breakout sessions is all gather here, and each of the people who are going to lead the breakout sessions will give you a quick 3-minute introduction to what they're going to cover. And then if you've signed up for something that seems inappropriate, you're welcome to switch at the last minute. We'll try to do load balancing so we have the appropriate numbers in the appropriate room. But we realize that not every topic is going to suit every person. So you're welcome to figure out what's what and then change as we go along. Right? And just let me say a brief few words about that now. The 3 sessions, one is on brain imaging and fMRI data, and then trying to understand what regions are causing which other regions in the brain. So the kind of data you get there is quite different from the kind of data you get in trying to figure out what the genetic causes of cancer or lung disease are. And so that kind of data involves time series, right, and all kinds of interesting measurement issues of converting a signal from an fMRI voxel to something that we actually take to measure, something interesting in the brain. So if you have different kind of research concerns from cancer, lung, or brain, but they involve a lot of time series measurements, I would think that going to the fMRI brain session would probably be the best for you. If you have genetics data, either microarray or SNPs or other kinds of data, I think the lung and the cancer sessions are likely best for you, even if you're not interested directly in lung and cancer. So what we're going to have in each of these sessions is several TAs, right, that are going to help with hands-on assistance like the sort we've been doing here when it comes time, especially for you to put your own data into the system and try to learn something about it. Right. So even if your data is a little bit off from the sessions in terms of how they're going, that's not a problem. Don't worry about it. Go to the sessions anyway, and we'll figure out what's what. Okay? All right. So today, right, we're going to change the direction, right? Yesterday we spent going from what it is to be a model and what it is to build a model and what it is to take that model and generate data from it, right? So that's, in my mind, models to data. And then today we're going to go the other way. We're going to start with data, and we're going to try to get you to, right, what model might have generated the data, or at least tell you what we can learn about the model that generates the data. And that requires some early work in trying to get us some bridge principles that connect these models and what they mean causally, right, to the kind of things we might observe in the data that will tell us something about causal as opposed to just association and correlation. And those bridge principles are the Markov axiom and d-separation. And I sat down last night and sort of thought about what I could really cover this morning productively. And last year I went really deep into d-separation and got all the way through it. And this year I really thought that that would prevent us from getting fully into doing hands-on search. So I've moved the d-separation deep part to the end of the morning if time permits. So I know some of you will be crestfallen and be devastated to know, but I'm happy to cover it at the end of the morning and happy to cover it later in the week if I can have time to do it. But we'll get through the very sketch of Markov axiom and d-separation early, and that will tell us how we bridge these causal models to what we could observe in data. And then we're going to talk about model equivalence, which is extremely important to motivate what it is that search could possibly tell us and what it is it cannot. All right? And so part of the project is really to tell us what you can know and what you cannot know from data and background knowledge. And then we're going to get into the model search stuff, and I'm going to have you do a lot of hands-on work in several different ways, building upon the same basic examples we had yesterday. Right? So all of those are going to end up, I think, helping you understand, right, what the search can do and what it can't in a very constrained, toy-like way. And then the afternoon we'll make the jump to realistic data sets, and then it'll be a whole different game. Lots of stuff. It's interesting. Okay. So the bridge principles, right? What we've done so far is talk about causal graphs and explain what it is we think they represent and what it is you mean when you actually write one down. And the first thing that I want to make sure you remember about them is they're entirely qualitative objects. There's no numbers associated with a causal graph. We didn't get to the numbers until we get parametric models and then instantiated those parameters with actual numbers. So the causal graphs by themselves, before we interpret them with a parametric model, are entirely qualitative. And therefore, right, it's appropriate if we can find a qualitative empirical relationship, constraint, prediction, etc., that would connect to these causal graphs and allow us to move back and forth, right, in some constructive way. And the one that's been studied the most and is really the cornerstone of the field is conditional independence. And if you can't see it in the back there, I apologize, you can look at the slides. But the way we notate conditional independence among variables is with this funny sign that looks like, right, a turnstile turned sideways. It means that x as a variable or a set of variables is independent of z given or conditional on y. Right? And what that means in intuitive terms, you can cash out in a million different ways. The way I tend to think of it is, once you know y, I've already told you the value of y, right? Then would it help you in predicting x to then also learn z, right? So you've already been told y, that's the conditioning set, and now you ask yourself, is z going to help me further predicting y, right? And I'll give you several examples where I think you'll see no, right? It's not going to help at all if I get if I get an extra piece of information. More formally, right, you can write out what it means to have a conditional independence relation, right, by saying the joint distribution of x and z, once I condition on y, is decomposable into the x given y and the z given y, right? So that's, right, formally what it means for all values x, z, and y, right? This relationship has to hold in order for the conditional independence to relate. But the thing that's worth pointing out is that this is a yes-no qualitative relationship, just like the graph has edges yes or edges no, so there's no amount of conditional independence. There's no amount of edge. It's just a yes-no thing, okay? So what we're going to get is a bridge from the causal structure to the conditional independence relation. And when I say that, I'm taking very seriously the idea that part of what the graph really means is how interventions play, right? So we did a lot of the modeling of interventions yesterday. And when I write this graph down here and say, why is that different from the graph that goes the other way, z causing y, z causing x, you can immediately intuit that the way those graphs would change upon intervention, right, is very, very different, right? So if I intervened on y in this graph, I cut out the xy edge, hard intervention. I leave this one in. If I intervene on y and the graph is going the other way, I cut out the zy edge but leave in the yx. So the way the graphs respond to intervention is what we really care about. And then connecting the graphs to something we can test so that the testing, right, tells us something about what would happen if we intervene is really the gold standard we're after. Okay. Okay, so the first thing to talk about in the causal Markov assumption that really does the connection is the weakest possible version of it, which we call the weak causal Markov assumption. And it's extremely simple, right? And you've, I'm sure, thought about it in one sense or the other already. It says that if two variables, v1 and v2, are causally disconnected, which I'll make precise in just a moment, then they're independent probabilistically, right? So there's no conditioning involved yet, right? So what does it mean to be causally disconnected, right? It means that v is not a cause of v1 directly or indirectly. v2 is not a cause of v1 directly or indirectly, and there ain't no common cause of both, right? So there's no way v1 causes v2, v2 does not cause v1, and there's no common cause. If those three are all true, v1 and v2 are causally disconnected. There are no causal relations between them. And we assume, right, to get this theory off the ground, that in those cases, that in the population, that v1 and v2 are simply independent, right? So you might have seen a million cases, right, where the contrapositive, right, so if I have v1 and v2 are associated, which is the opposite of independent, right, then, right, we want to assume that they're causally connected. right? And there's lots of cases where there's some weird correlation between the number of times, between whether or not the NFC wins the Super Bowl and the stock market goes up or down, right? Or between the number of times Nicolas Cage is in a movie that year and yogurt sales go up or down, things like that. And then those challenge us because if we try to say, well, gee, Nicolas Cage movies and yogurt sales are correlated, right? So that's negation of this. Then that means Nicolas Cage and yogurt sales must be causally connected. Okay, tell me how Nicolas Cage movie sales, right, and yogurt sales could be causally connected. Anybody have a theory? Summertime. Well, there's a good, but no, it's over the whole year. So one summer versus, right.
Wage increase.
What?
Wage increase.
Wage increase, right.
So, have money to see that.
There always is some story you can tell, although not always. But another explanation is this is literally just, right, some sample coincidence, right, that's true of the last 10 or 15 or 20 years. And if we reran the world enough times, that would disappear. So it's not really an association in the population when we think about what the population really might mean. Okay? But that assumption amounts to, right, if there's an association, something causal is producing it. Right? It's the same thing. Okay, so if we accept that assumption, the weak causal Markov assumption, and we accept this account of causation that's deterministic, so we have structural equations of the sort that I showed you yesterday, both in the SEM and the generalized SEM, right? Then those two accounts together produce the causal Markov axiom, which is the general connection, right? And I'm not going to go into it in any depth, but you have a G as a causal graph, and you have P, a probability distribution over the variables in G, and that pair, graph and probability distribution, satisfy the Markov assumption if every variable is independent of its non-effects when I condition on its immediate causes, right? More easily, we can actually understand the connection by taking the causal Markov axiom that I just showed you. If I have graphs that have no cycles in them, then together those imply what's called the dependence separation criterion, which is entirely calculable or computable just by giving you a graph. It's very easy in a certain sense once you know it. And the deseparation criterion gives you, right, the connection that's easy in general from a causal graph to a graphical independence oracle. So you give me the graph, I take deseparation, and I can read off like an oracle every independence and conditional independence relation that's implied to hold, no matter how I parameterize the graph, and no matter what values I put in the parameters. It's totally general. So for example, if I have this graph, right, and I say, okay, what independence relations ought I expect to hold in any probability distribution that I could parameterize with such a graph? And there's the answer. At least those, because those are all entailed by the Markov axiom and hence by deseparation, because this is an acyclic graph. So everybody understand what an acyclic graph is? Yeah, it means there's no way to get from one variable causally back to itself. There's no cycles. And when you think about what a cycle is, right, that's a complicated notion that requires us to be generalizing and collapsing over time. Because I think it's a perfectly reasonable thing to assume that causal relations take time to happen, right? So if I change something, right, X, right, it's going to take time before whatever it causes, Y, to change as well, in distribution or in value or what have you. Once that is an axiom or assumption, right, then I can't have strictly cyclic graphs. So when I have a cycle from some variable X back to itself, it's sort of a shorthand for, right, in general, right, if there's some property of something X and I wiggle it and it changes other things, it might change back to the same property X at a later time, right? So it's more like X causes Y a time later and Y causes X at a time later. But X at a time later and X at a time now are strictly not the same variable, right? So to treat them in the same variable is, there's a lot of shorthand going on there that requires some explication and it actually matters, okay? But these are the relationships, right, that have to hold no matter how I parameterize this causal graph. So that gives me a big purchase, a big handle, right, on graphs if I can get independence relations. So now you can see the strategy here, right? This, right, is in the province of we can look at data, right, and we can test for these relationships. We can get at that, right? That's statistics. And then if we can get at this, and we have this relationship, then we should be able to reverse engineer, like, what are all the graphs? All the graphs that give me that set of independence relations as a consequence of the Markov assumption, et cetera, et cetera. So that's the basic strategy. And that leads to this next notion of equivalence, because if I have more than one graph, right, that implies the same set of independence relations, then they're said to be Markov equivalent, right? And independence relations alone could not distinguish between those two graphs. So we now have to characterize and understand precisely when two graphs, right, are equivalent in the sense of they make the same predictions. Right? So there's going to have to be something else we do besides look at those predictions to tell those graphs apart. Even though we really think when they're two different graphs, they say different things about what would happen in the face of interventions. They don't say different things about what we should observe in terms of the constraints in the data. So we're in a pickle, right? But we're at least epistemologically enlightened if we can tell you these two guys cannot be distinguished.
I'm sorry, can you say what you said again at the beginning about they don't have the same properties, but they have the same output for equivalence?
Sure. So if we go and we look at the deseparation relation criterion, and we say, give me a causal graph, and then I can generate what predictions it makes. And then I say, suppose I give you a different causal graph. That's going to have different consequences in terms of intervention.
Oh, like what we did yesterday.
Yes.
The output or the outcomes.
But it will have the same consequences, perhaps, in terms of its predictions. So, I mean, in the simplest possible case, right, if I apply this theory to two graphs, right, they say very different things causally, right, especially intervention. If I intervene on X, right, Y wiggles, doesn't here, and vice versa. So they are different claims about the world in terms of intervention. They don't say anything different about independence. They say nothing's independent of anything, right? X and Y are, right, associated. X and Y are associated. There are no other variables in the system. So in some sense, this is the totally trivial observation that correlation is not causation, right? Okay, so independence, right, is only one kind of prediction that we might look at. There are others, right? So when I say two graphs are independence equivalent, that doesn't mean that they're perfectly equivalent, because there might be other predictions those graphs make about the data that I could then use to distinguish between those graphs. But it's very handy, and the whole field started off by looking at independence equivalence and saying, what does that look like? What does that amount to? And so, in general, the distribution, the difference between independence equivalence and distribution equivalence is formalized here, right? This is independence equivalence. Model 1, right, which I take to be a causal graph, and model 2 are independence equivalence if, right, when model 1 entails a conditional independence relation by the Markov assumption and deseparation, then model 2 entails the same relationship and vice versa. So that's what it is to be independent equivalent. Yeah?
So, can you determine the independence from the data itself without knowing anything about the graph or?
Yes. So that's a completely statistical decision. So if I give you a data set, right, and I ask you, here's some variables, and I say, what's independent of what, right, you can test that under a variety of parametric assumptions or non-parametric assumptions, right, but that's a purely statistical act.
So that's not what deseparation is?
No. Deseparation is getting you what independence facts are implied or entailed by a graph. So deseparation says, here's my theory, here's my causal idea, what predictions does it make in terms of independence? And then to see if those predictions are true in the data, you got to hire a statistician. That's the statistician's job, to make sure that we have data, so we have sample relationships, and then can we infer from the sample what's true in the population? And that's an independence kind of decision. Okay? So it really is trying to get from, right, causal theory to a testable prediction. And that's the whole key of deseparation. Okay. Is that clear? Okay, so that's the idea of independence equivalence for two models. And this is a more complicated idea. It's called distributional equivalence. And this says that if I have a model, M1, which is a graph, and I parameterize it, right, like we did yesterday, right, and then I have the parameters for that model theta 1, and I have a second graph, M2, and I have the parameters for that theta 2, then those graphs are distributionally equivalent, right? If for every parameterization I could stick in theta 1, there's some parameterization theta 2, right, so that the distribution induced are the same, completely the same in probability distribution terms, right? So that's not true for, there's many, many graphs that are independence equivalent, but that are not distributionally equivalent, right? Especially when they involve latent variables. So here's a simple example. So if t is a latent variable I don't get to observe but is acting like any other, and it's a common cause of four variables that I do measure, x, y, z, and w, then there are no independence relationships entailed about x, y, z, and w. They're all associated, and they're all predicted to be associated conditional on each other or in any subset of each other. So every possible conditional independence relationship, right, among just the measured guys does not entail, is not entailed, right? So there's that. And here's another one. There's another graph, right, that entails the same independence relations, namely none, right? There are no independence relations entailed by this graph. So these two graphs are independence equivalent over just x, y, z, and w. They're very distributionally different, right? There's many, many distributions, right, that I can parameterize with this one that I cannot parameterize with that one. Okay? And there's a million other examples. And we're not going to go into anything sophisticated about distributional equivalence, but I just wanted to make you aware that when you say, let's look at the independence relations and figure out what graphs we can figure out might have entailed those, that's not the end of the story, right? And there's been a lot of work since then on extending what we can learn past the independence equivalence relationship. Okay, but what we've managed to do is a lot of interesting stuff about equivalence just using deseparation and independence, right? And I'll go into the patterns fairly detailed in a few minutes, and we'll go into partial ancestral graphs a little bit tomorrow. So patterns, right, are equivalence among, independence equivalence among graphs in which there are no latent confounders. We're just talking about a certain set of variables, and then assuming there are no latent common causes. Partial ancestral graphs relax that assumption and allow us to talk about equivalence even when we've left out latent common causes, right? So this is a big jump, right, into warp drive of a certain type. And then in intervention equivalence classes, right, goes into when could we not distinguish independence-wise between two graphs, even if we were given interventions and allowed to intervene, right? So that's another very interesting idea. And then I'll talk a little bit, but probably not a lot, about an idea that's very interesting in psychometrics and educational research where they're trying to figure out like how much ability in math or how much ability in reading or how much analytic ability or how much algebra ability people have, and they give them lots of items to answer, like algebra items, or they give you lots of questions like, you know, how strongly do you agree or disagree with the following statement, right? I can never sit through a full movie without getting restless, things like that. So they build measurement models to actually figure out what latent variables, right, are out there and how to measure them. And then we can characterize measurement model equivalence under a whole variety of assumptions. And then there's this very interesting theory that's evolved in the last 10 years in which when we have those linear models I looked at and we worked on yesterday, right, but the error terms are non-Gaussian, right, they're skewed, they can't be symmetric in distribution, right, then the equivalence class is very different than the equivalence class for independence. In fact, we can distinguish every graph without latent variables. They're all unique in terms of what data constraints they would actually entail, which is a fascinating fact. Okay, and there's many other ideas about equivalence. But when we now go to just independence equivalence, which is all I'm going to really focus on now, right, there's a couple of key ideas. And one key idea is a collider versus a non-collider. And so now it's going to get easy and you're going to have, I think, your graphical intuitions provoked. So in this case, right, y is said to be a collider in between x and z. Why? It's because the arrow from x to y and z to y collide at y. Right? So it's a common effect. Right? In those three cases, the graphs have the same skeleton or the same adjacencies as the first one, but they don't have a collider at y. So in the first case, y is a collider, and in cases 2, 3, 4, y is a non-collider. Okay? So you need to get that distinction in your head and be able to actually compute it. Okay? So, right, non-collider, non-collider, non-collider. There's three ways, right, a variable can be on a path and be a non-collider. There's only one way it can be on a path and be a collider. Okay? So when y is a collider in this kind of a situation, right, we ask whether x and z, the guys that point into it, are adjacent or not. Have I defined adjacency? Adjacency just means that there's some direct edge between those variables either way. Right? So x and z are adjacent, and they'd still be adjacent if z caused y directly. I mean, z caused x directly, as opposed to x causing z. Right? So any kind of direct edge there means they're adjacent. So y is a collider, and it's shielded because x and z are adjacent, and here it's unshielded. That's simple. Right? Everybody got that? And so here is the first big result in this field. I think it's safe to say, or among many. We call it the deseparation independence equivalence theorem, and it's from Thomas Verma and Judea Pearl, late 1980s. And it says that if we have two acyclic graphs, right, and they're over the same set of variables, then they're deseparation equivalent, which means they imply the exact same set of independence relations. Right? If and only if they have the same adjacencies and the same unshielded colliders. It's really that simple. Right? So if I give you two graphs and I ask you, do they have the same adjacencies? Do you think you could answer that? Yeah, you should be able to answer that. It's just the same, right? When I take away the arrows in the directions of the arrows, do they have the same basic connections, same skeleton, same undirected arrows? And if they have the same unshielded colliders, then they're equivalent in the sense they imply the same set of independence relations. And so if all we could observe were those variables and all we could test was those independence relations, and we couldn't do any interventions, we couldn't measure anything else, we could not distinguish among those graphs. Nothing you could do. Okay, so now I'm going to go, yes?
So for example, in two graphs over the same variables in which every arrow is just reversed, they would be deseparation? Oh, sorry, the colliders.
I don't think necessarily that's true.
Colliders would make that false.
Right. In some cases they would be equivalent, in some cases they would not. I never thought about that. It's an interesting question. It's certainly the case that if I looked at something like this, they would be equivalent. Right? In many of the cases. The question was if I took two graphs, right, that had this, if I took a graph and I reversed every edge, would I remain in the equivalence class? Right? Is that the question? Sorry, that's the question? That's not true. So if I had that graph, right, and I reversed every edge, I get to that graph. That is equivalent. It has the same adjacencies and it has the same unshielded colliders, namely none, right? But if I started with this graph, and I reversed every edge, right, I now have the same adjacencies, but I do change from an unshielded collider Y to an unshielded non-collider Y. So these are distinguishable. Right? Okay. So that's the basic idea, and we're going to come back to that in a second and actually give you a little bit of experience. But first, I just want to go right to the program and have you do the same and actually see how this might be something testable. So we're just going to go create a graph, and we're going to generate data from it, and we're going to do an estimate of the model. And then we're going to take the same graph and flip an edge to make the graph equivalent, and then do a different graph where we flip an edge to make it non-equivalent. And then go ahead and generate data or test each one and make sure, all right, it's distinguishable. So this is the same thing I did yesterday, right, with the 4-variable graph, but let's just do another one. So let me show you something else that's handy. If I go up into the template menu, right, there's lots of different templates, and one of them is I could estimate from simulated data, and that just pops in the, right, all the boxes I need in one shot. Oh. Good, better. Sorry. Let me go do that again. So if I go to the menu, right, that says template at the very top, and I click on it, there's many options. And if I click on one of those, for example, the estimate from simulated data, right, it just pops in all the boxes and the arrows I need to actually build that kind of a system. So if I build a graph, right, with 4 variables, and I build all sorts of any kind of relationships there, right? That's one of the options I could do. Send parametric model, and I instantiate it, right, etc., and generate data, estimate that data, and go to the model. Okay, I get a p-value of 0.3446, chi-square of 3.3219. Okay, so that's my starting point. And now, my question is, right, what graphs can I build that will be A, equivalent to this, and B, not equivalent to this by changing only one edge? Okay? So what I'm going to do is, right, I'm going to build the setup for that. Like this, and I'm going to say, for this graph, graph 2, let's flip one of the edges but make sure it's equivalent. And for graph 3, let's flip one of the edges to make sure it's not equivalent. And now that you have what it is to be equivalent, right, you can win that bar bet, and you can actually predict what's going to be what. Okay, so let's start with graph 2. So let's flip an edge and make this equivalent to the model that I've already started with. Which edge can I flip? Turns out only one of them. The x1, x3 edge, right? If I flip the x1, x2, right, I've got a collider here that's unshielded, all right, but I'll now change it into a non-collider. So that'll be unequivalent. But if I change this one, right, the x1 is already a non-collider, and I keep it a non-collider. Now there's an easy way to flip an edge. You just click on the side of the edge. You want to make the arrowhead like click. It flips the edge, click, it flips it back. So that's a handy thing to know as well. Little interface trick Joe did. Okay, so if I say that's my graph, save it, it says, yeah, let me execute that, right? And that should be, right, the exact same model fit statistics as the original guy. And it is. Chi-square of 3.3, 3.3, p-value of 3.446, p-value of 3.446. Okay, so that's an equivalent graph. Now let's go to the same starting point, but flip one of the edges that's non-equivalent, right? And that's either of the x1, x2, x2, x4. So let's flip the x2, x4, say execute. And now when I go to this, right, the p-value goes to 0. It's quite powerful, right? I mean, you don't get, it's not like a subtle difference. Like all of a sudden the model just completely doesn't fit, it's disaster. So I want you guys to go ahead and do that so you can get your head around. Start with the graph, right? And then do two changes to that graph that are one-edge perturbations so that one perturbation preserves equivalence, keeps you in the equivalence class, and then the other one-edge perturbation takes you out of the equivalence class and makes it into a non-equivalent structure. Okay? Everybody good? Go ahead and we'll walk around and help.